All right, y'all. In this video, we are going to cover the rest of the 3.2 exponential functions lesson. We're going to start off here with just talking about what E is. And you guys have used this number before. However, it's probably been a little bit. E is similar to pi in the fact that it's an irrational number that's just, it's never going to end. And it is a constant as well. This is how E is calculated. So if you're wondering where it comes from, it is coming from that limit that you're seeing here. I'm not going to ask you to calculate that or to show me how all of that works. However, that's what it comes from. And this is the number that is resulting. It is a number that never ends, and we usually round it to be about 2.72-ish, okay? And that's the number that we use for E. E is used in a lot of different exponential functions, and so that's what you're about to see. So exponential functions and base E, right? We've talked about like growth and decay in the last video. We talked about them for just typical exponential functions. However, we did not talk about them in relation to E. Now, we need to talk about this a little bit because we can write exponential functions with E as the base, okay? But we need to bring in this value that we're going to multiply by x. So this is a k, if you can't read my handwriting. This is saying k times x as that exponent. And k is going to be there to help us to determine if it is exponential growth or if it is exponential decay, okay? So we're going to look here, and in both situations, we're going to say that a is positive, okay? If a was positive and the k value is also positive, that means this is exponential growth. And the reason for that is, I want you to think about this. When we had the a times b to the x, right, we said that if b was greater than 0, it was, sorry, not greater than 0, greater than 1. If it's greater than 1, then we had growth. If b was between 0 and 1, it was decay. So I want you to think about the number E right now. The number E is 2.72-ish, right? That is more than 1, meaning that when E is the base, that would naturally be exponential growth because that B value, the base, was more than 1. Here's the thing. If that exponent happened to be negative, I want you to think about what we would have. If I had E and it was to the negative x, remember what negative exponents do is it decides to drop E into the denominator. So this would end up giving you a situation like that. Imagine this is 1 over 2.72, right? And when that value is between 0 and 1, that is when we know that this is decay. And 1 divided by 2.72, that's going to be between 0 and 1. That would be decay. So whenever you have a negative exponent, it results in decay when you have exponential with base E, okay? All right, so that's what you're seeing here. We're going to do a few examples just to practice talking about those transformations, and we're also going to talk about graphing these guys, all right? So that is what you are about to see. Okay, so they said we're going to talk about transforming from the parent function there, where it's f of x equals e to the x. Then we're going to graph both of the functions, so e to the x as well as the one that's indicated. All right, so we're going to talk about the transformation part first. All right, guys, if this is e to the 2x, right, that 2 is being multiplied by x. And when that's the case, we end up seeing a horizontal dilation, okay? It's being multiplied, so that tells me a dilation. And because it's happening just to the x, that's happening to those inputs affecting the x values, and that's going to cause this to change horizontally. So with that being the case, we're going to say this is a horizontal, I'm just going to abbreviate a little bit here, horizontal dilation. Now remember that horizontal dilations are a little bit weird. Anything horizontal is a little bit weird. And when you do a dilation, you have to flip that factor, that value here. So this is of 1/2, okay? Now, they said to graph both, so that's what we're about to do next. Let's make ourselves a little graph grid, and then we're going to talk about what these look like. Okay. All right. So first things first, when we graph these, and we're going to kind of do a little playing around with the graph thing for a minute. On my calculator, I've gone ahead and inputted these two functions, e to the x and then e to the 2x. All right, now you're going to see that e to the x, this is that magenta color. I don't know if you can tell very well on your screen, but over on the far left, it kind of shows. E to the 2x is blue. The parent function is that reddish color. So we're going to go up here to the graph, and we can see what those look like. The red color, remember, is the parent function. The blue is the one for G, which is what I'm seeing here. And that should make sense because the blue one is closer to the y-axis because it shrunk it in, right? You think about how that works. If it shrinks it in, right, it shrunk it horizontally, meaning it should be closer to the y-axis, okay? What I'm going to do is sketch this a little bit. Now you can tell that both of these have gone through that y-intercept where that y value is 1. So that's a nice little feature that they both have. But other than that, they are very different. Okay. So I'm going to zoom this back out so you can see the graph once we graph here. Okay. So I'm going to put our little parent function, e to the x, I'm going to put it in that kind of same color, reddish color. Okay. Now, both of them, again, are going through that little point, but the e to the x is a little bit further out. That was our function. F of x is e to the x. Okay. However, the g function, I'm going to do that here in this blue color, it also went through that, but it was closer to the y-axis. Okay. Because it was horizontally shrunk. So that blue one I'm putting as my g of x. Okay. All right, let's try our next one. Our next one here, it says we have e to the negative x. Well, that negative has decided to reflect this. And because it is with the x, that reflection has happened across the y-axis. Okay. And we'll be able to see that. Let me put it in the calculator. I'm just going to go in here and change that one little thing. So go back to those expressions. We're going to change this guy to be a negative as the exponent. And you'll be able to see that flip right there. The red one is, again, the parent function, e to the x. The blue one is the one that has been reflected. They are both going through that same y-intercept. So I'm going to make sure that that is showing on my graph. They're both going through that value of 1. Let's put our parent function on here first. Again, that's going to be going up something like this. That is my f of x is e to the x, right? That was the parent. But this guy looks exactly the same, just a mirror image. That was h of x. Okay. All right, one more of these. We're going to look here at number or letter C, where we have 3 times e to the x. Okay, well, 3 times e to the x, this is showing a number times the whole function. Well, whereas back here on part A, that number was multiplying just to the x. That was a horizontal dilation. This one is multiplying times the whole thing. That makes this a vertical. Vertical dilations, you don't have to flip. So we're going to say that vertical dilation, and we're going to say of, that's so crooked, a vertical dilation of just 3. Okay? Make our little graph grid again so that we can graph these guys. Let's see what this looks like. The parent function is not going to be any different, so just bear that in mind. But when I go up here and we change the second one, there is some change on this. Okay. So that first one is still going through the value of 3 on the graph. So that's my parent in the red. That's f of x, right? Whereas the blue one, it's not only that it's closer to the y-axis there, it's actually going through the y-axis in a different place. If you go on your calculator and make it show you, it shows you that it's hitting the y-axis at 3 instead. And that should make sense because it's been stretched by 3, meaning it's pulling it further away from the x-axis. Okay, so that's going to go through that value up there. And this thing is a little bit placed different. Looks something like that. So that is my k of x. All right, so graphing those functions, seeing their transformations, that's what I'm looking for. Show me those intercepts, show me how they change or how they're different. Label them, all right? Make it clear which one is which, and that should be good. All right, the next thing we need to talk about is logistic functions. Now, before I go through this completely, I want to talk about logistic functions. We have studied them just a tiny bit before. Okay, so you got to remember back to a old section. I think this was back in like 1.2 or something like that. I can't remember exactly the section. It was back in chapter 1. But the logistic functions were those type. They had an interesting shape. They had 2 horizontal asymptotes. I don't know if you can see this very well. It's not very dark. That's a little better. Okay, so they had 2 horizontal asymptotes, and the figure had like an interesting shape. It kind of started off as exponential, so it has that curvature going up, concave up, but then somewhere along the way, it shifts and becomes concave down, and it approaches both asymptotes on either side, right? So it had an interesting shape. We're going to study these a little bit closer now, okay? But logistic functions have that way. Now, they naturally are going to have an asymptote at y equals 0, but they're also going to have another asymptote up here, okay? And we're going to talk about how you can find that one really, really easily. Okay, so I'm going to give you some notes, and I may bring back that sticky note in just a moment. But this is stuff about logistic functions. I would maybe pause the video so that you can get all of this down. Let's see. There you go. All right, pause the video. Start getting this stuff copied down and then come back and we'll go over it. So logistic growth functions are going to have this pattern here where we're dealing with the A, B's, and C's. What you're seeing, they're going to be positive. Okay, K is positive, constant. But your B would be less than 1. Okay, so in this scenario, we've got 2 different types of logistic growth functions. We have one where the base is a constant B, like that. And then one over here where the base is E, which is a constant, but it's kind of a special constant. Okay, so they're kind of treated differently. I want you to make sure that you keep them individual. This one uses the B as the base. This one uses the E as the base. In both situations, you're going to see this C on top, okay? And that C is what we call the limit to growth. And that means that is the cap. That is the highest the thing could go, okay? Which means on my little scenario over here, we get an asymptote right there at that C value. So we have 1 at y equals 0, unless it's been shifted up or down, that's the case. And then we're going to have 1 at that C value. Okay, so I'll bring that back in a minute when we need it again, but just keep that in mind. You can always add that as a picture to help you if you wish. Okay, let's see. We've got decay sometimes, but it's not super duper common. What you'll notice about logistic decay is if it's that first type, that B value is going to be more than 1. If it's that second type with the E's, you're looking for a k value that is less than 0. Okay, so negative. Most of the functions we deal with are going to be growth, but there. We also have kind of your basic logistic growth where everything is very, very simple and plain, and we can kind of see like what everything is based off of on there. So you would be seeing an asymptote at 0 and at 1, and then it all stays within that. So that's the one that we've seen before, but we're going to kind of see these how they're different. So example 5, it says that we're going to find the y-intercept and the horizontal asymptotes, and then we're supposed to graph this, right? It says graph it. We're going to have to graph it, and it does not mean just throw it in a calculator. You can totally do this a little bit by hand. So I'm going to show you how that's going to look. We need to decide a couple things, such as what is the y-intercept, what are the asymptotes, and then we have to make a decision on if it's growth or not. I said most of them are growth, but that's not guaranteed for every single one of them to always be growth, okay? So let's look at this right here. We've got a function where we see the first situation is like the first situation in your notes above where you're not using an e, right? I'll bring that back. It's like this one. We're not using an e. It's using another number. So on part A, it's going to be like that scenario. So for us to decide things, we need to first of all look about our y-intercept. So on your y-axis, on your graph, on your y-intercept, your x value is 0. So for you to find that y-intercept, all we got to do is plug in a 0 to the function, and we'll be able to find where your y-intercepts are. This is 1 plus 3 times 0.7 to the 0 power. Well, here's the deal. Anything to the 0 power is always, always, always going to be 1, no matter what. I don't care how ugly it is. So 0.7 to the 0 power, that's going to give you a 1 down there. We get 1 plus 3 times 1. Well, this is 1 plus 3 is 4. 8 divided by 4 is 2. So I get a y-intercept to add 2. So there's the first thing I need. The second thing I need is I need my asymptotes. So let's find our horizontal asymptotes, right? We're going to say y equals, and the first one is always going to be y equals 0. Unless this thing had shown like a transformation up or down, y equals 0. That's the horizontal asymptote. But there's another one, and that other horizontal asymptote just comes from that top number, 8, because that is the limit to your growth, okay? So that's important. The other thing I have to decide is this a growth or a decay, okay? So we're going to kind of separate that. We're going to say, is this a growth or a decay function? Well, I need to look at that b value, right? We said in that scenario, if it was decay, has a positive, has a value that is more than 1, a b value more than 1. Whereas with the growth function, the b value was less than 1. So we have to decide this b value. Is it more than 1 or less than 1? This is less than 1. So because 0.7 is less than 1, it's growth. Okay? So we're going to graph this, and it is way more simple than it sounds, all right? We have all the components I need to get a sketch of this thing. So we're going to do that, okay? All right, we know that we're going to have a horizontal asymptote at 0. So I'm going to kind of put that in this color right here. We're going to have a horizontal asymptote there at 0, and we're also going to have one up at 8. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. Okay, up there. Okay. The other thing is we are going to have this hit the y-axis at 2, right? It's the y-intercept is at 2. So I'm going to go here and put a point. The other thing is we know this is growth, meaning it's going to go up. And on the left, it's going to go down. That's a decent enough sketch for me. Okay? All right, let's talk about this guy, B. Okay, so same deal. We are going to figure out our intercepts and our asymptotes. But what I want you to notice about this guy is we are dealing with the one with an E on it, so things might be a little bit different. We're going to go based off of this second thing where we're working with that E, okay? All right, so first things first, y-intercept. Same deal. You are going to plug in a 0. So that's what I'm doing. This is 20 over 1 plus 2e to the negative 3 times 0. It's a lot to write, kind of small. All right, we got 20 over 1 plus 2. Now this is e to the negative 3 times 0. Negative 3 times 0 is 0. E to the 0 is 1. So this is really, 20 divided by 3, which is about 6 2/3. Okay, so we can use that. You could also change it to a decimal if you would prefer a decimal, but okay. Asymptotes, horizontal asymptotes. We got one at y equals 0. The other one is at our limit of growth, so that is at 20. All right, the last thing I have to decide is this growth or is it decay, right? So we're going to have to determine that. Well, remember how we said on these, if this is my scenario, right? For growth, the k value is positive. K is positive for the growth function. Now for the decay, k was less than 0, okay? So for my decay, k has to be less than 0. I'm going to look at my k value on that thing. Now, see this value in front of x? That's a negative 3, right? Let's separate this. That negative 3 is the same. See the thing in front of x, negative 3. Well, look at the thing in front of x, negative k, right? If negative 3 equals negative k, that means 3 equals k. So k is actually positive, which allows me to say that this is growth. Okay? Now let's graph it. Make this one a little bit larger. All right, we're supposed to go up to 20. Now I'm going to make this be 5, 10, 15, 20, like that. And we're going to show that asymptote in there. So again, we have an asymptote on the x-axis down here. We're also going to have an asymptote up here at 20, like that. The other thing was to see where my y-intercept is, which is at 6 2/3. So we're just going to say a little bit above the 5. We also know this is growth, so it's definitely going to go up, just like that. All right, guys, we got one more thing to do. All right, one more problem we're going to go over, which is, look here, example 6. Using the table and assuming the growth is exponential, when did the population in Austin, Texas surpass 1 million? So we've been given a table here, right? And on this table, we have been told different, we've been told population, we've been told a time, okay? So that time is in years, and the population is for this city of Austin, Texas. Okay, so what we're going to do with that is we are going to use the values that they've given you, and we're going to create an equation to represent this. Now, they said to assume that this was exponential growth, right? So we're going to be allowed to make that assumption because they said I could. But we're going to have to figure out the equation that we're going to use for that. So first thing I'm going to do is So I wrote the table back down so I can mark on this and I don't mess up my paper. But a really important thing for us to do is remember what our basic form for an exponential is. Okay, that is y equals a times b to the x power, just like that. And we are going to plug in values. Okay, now it's a little bit tricky, but what I think we're going to do with this, I think it's going to be easiest, is to allow the first piece of data that I have, I want to allow this to be my initial starting point. We're going to let this be the initial place because that is the first value. Okay, so we're going to let that be the initial one where your x is 0. Okay, that would mean that this guy would be like the population when that was 0. It's the y's, okay? We're going to let these kind of be the x's and these kind of be the y's and kind of go along it that way. Now, here's the deal. If this guy was x equals 0, this one would be x equals 11 because it's 11 years after 2010. So this guy would be p of 11, okay? So just keeping that in mind, right? We're letting this kind of be my x and my y. And my y's, this is like the p of x type of situation. X and p of x. Okay, so remember what we've said about the initial value. The a value on an exponential, that's your initial value. So at my initial value, the population was 815, right? 815,974. 815,974 would be my A. So we'll say y equals 815,974. That's the A. We don't know the B, and that's to the x power. So right here, this is kind of me starting to write the equation. I cannot figure out the answer to this until we get an equation written. So we're going to write an equation, right? But to be able to get this, I'm going to have to find what the B value is. Okay. And I can't do that without using my other piece of data. So what we're going to do is remember how each of these is like an X and then a Y, right? X and then a Y. So what we're going to do is actually plug those in for the X and the Y's that are in my equation here. We're going to let this be when X is 11 and this be the Y when X was 11. So I'm going to plug in the 964,177, 815,974, right? B to the what power? Oh, yeah, that was X, the 11th power. And then we solve this out. Okay, so I'm going to let this take up the screen. We'll come back to the problem in a moment when we need it again, okay? So this is kind of separate. I was just trying to fit it all on the screen. In order to solve this, I need to divide both sides by the 815,974 cancel by. That's going to leave me with this ugly fraction, and I'm going to leave it as a fraction for the time being. 964,177 divided by 815,974. That is equal to b to the 11th. Well, in order to solve that, y'all, we have to do the opposite of raising something to the 11th power. The opposite of raising something to the 11th power would be rooting using an 11th root. Okay? And that's something that we can all type into our calculator and get an answer. Okay? So I've gone ahead and done that on here. Already ready to go. Look at that. We have the 11th root, and that gave me this nasty decimal. So I'm going to write that out. Okay? B is 1.015287716. 6. Now, remember how we've said we don't want to round until the end if we can avoid it. So, although the calculator did round this number, I think it's fair to just say we're going to write that whole thing out. And then we will round the thing at the very, very, very end. Okay, because this is not the final. And if I round too early, things will get off. Okay, so what we're going to do with this is we are going to then finish writing our equation. Remember that whole, I'm going to have it right there, y times a, or y equals a times b to the x. Well, we just found b. We already knew a. Now we found b. So I can write an equation, y equals a times b to the x, right? We're going to say this is p of x. That's my y. That is equal to the a value, which we said was 815,974, times b, which is this nasty decimal, 152,877,16 to the x power. That is the equation we can use to figure out anything for this predicted population growth, okay? So here we have a lovely equation. Remember what the question said? When did it surpass 1 million? Okay, so what we're going to do is plug in 1 million for my population. You might be thinking, oh my gosh, when is the problem going to end? It will be over soon, okay, I promise. We're going to plug in 1 million, okay, for the population. 815,974 times 1.015287716 to the x power. Okay. And because we haven't practiced with logarithms yet this year, I'm going to say that we are going to be allowed to type this in the calculator. Okay. Now, the way we do that is on one of the functions that we type in, we're just going to type in 1 million. Okay. And on the next one, we're going to type in this whole thing that you're seeing right there. Okay. So open up another function and we're going to type what you see. 815,974 parentheses 287716 close to the x. There we go. And I want to see where they cross. So these are crossing over here. Might be kind of hard to see exactly where they cross. It looks like that might be it, but it would be best if we actually go to the calculate thing and tell it to find the intersection. And it tells us right here, it is at 13.40-ish. Okay. So we're going to say x is about, this is the moment where I'm allowed to round because we're here at the end of the problem. 404. All right, so what did that represent? Well, that represented the years past my initial. All right, so we're going to add the year to 2010. So this is the year 2023. Okay, in the year 2023, that's when it's going to surpass 1 million. Okay. So I know that was a little bit more, there's a little bit much, but that is it for that second part. Guys, that wraps up section 3.2, and I will see y'all in the next video. Bye.